is more than 1. So from the whatever is the scenario, the C will take that much of value depending on the number of servers. The queue discipline or service discipline is on first in first out basis. Capital N denotes that there is a restriction for the number of customers to be present in the system, and that is a finite number N. Again, from the scenario, we will identify what is the value of N. And the last letter infinity indicates that the size of the calling source population is infinity or infinite. Various parameters for this queue model. We can find out probability of having 0 customers in the system as P0. There are 2 formulas. One is if rho divided by C not equal to 1. Another one is if rho divided by C is equal to 1. Rho is nothing but lambda divided by mu. So if it is not equal to 1, the formula is summation n equal to 0 to C minus 1, rho to the power of n by n factorial plus rho power C times 1 minus of rho by C to the power of n minus C plus 1. This divided by C factorial into 1 minus rho by C. If rho by C is equal to 1, the formula will become P0 is summation n equal to n equal to 0 to C minus 1, rho power n divided by n factorial plus rho power C times n minus C plus 1, the whole thing divided by C factorial. This entire thing to the inverse. Even here also, the entire thing to the inverse. And the steady state probability of having n customers in the system can be calculated as Pn. Again, if small n lies between 0 and C, this will be the formula. If small n lies between C and capital N, then this will be the formula. That is, P suffix n is rho power n P0 by n factorial in the first case. And the second case, it is rho power n P0 divided by C factorial multiplied by C to the power of n minus C. We can calculate the length of the queue or average number of customers waiting in the queue in this model as L suffix Q is equal to. Again, there are 2 formulas. If rho by C not equal to 1, if rho by C equal to 1. If it is not equal to 1, then we use P0 times rho power C plus 1, the whole thing divided by C minus 1, the factorial, times C minus rho, the square. The whole thing will get multiplied with this. What is that inside the brackets? 1 minus rho by C to the power of n minus C minus n minus C times rho by C to the power of n minus C times 1 minus rho by C. And if it is equal to 1, then we use P0 times rho power C, n minus C times n minus C plus 1, the whole thing divided by 2 times C factorial. Then we can calculate the average number of customers waiting in the system as L suffix S equal to LQ plus effective lambda divided by mu. What is effective lambda? Effective arrival rate of customers, which can be calculated as lambda times 1 minus P suffix capital N. Average waiting time of customers in the system can be calculated as WS equal to LS, whatever we calculated earlier, divided by effective lambda. Similarly, average waiting time of customers in the queue can be calculated as WQ is equal to LQ divided by effective lambda. Then we will do one problem now. In this, in a harbor, ships arrive with a mean rate of 18 per week. The harbor has 4 docks to handle unloading and loading of ships. The service rate of the individual dock is 6 per week. The arrival rate and service rate follow Poisson distribution. At a point in time, the maximum number of ships permitted in the harbor is 6. Find the standard results of this system. So first we have to identify the model. Given that the arrival rate and service rate follows Poisson distribution, which means the first 2 letters of the queuing model will have M in it. The harbor has 4 docks specified to handle unloading and loading of ships, which means 4 servers. So the third letter will have C, and in this problem, C will be taking a value 4 because it has got 4 docks. Then nothing is specified about the service discipline. So the in the queuing model, the 4th letter will be FIFO only. Since there is a restriction for the number of ships permitted in the harbor is 6, the fifth letter will be capital N, and here capital N's value will be, sorry, here it should be 6. This should be 6. Then nothing is specified about the size of the calling source population. The sixth letter in the queuing model will be considered as infinity. So finally, the model will be MMC, FIFO, N, infinity. So we can use those parameters, whatever we saw, for solving this particular problem, because we need to find out all, in this question, they say, find out all the parameters. Find the standard results of the system. So that means we need to find out all the parameters. The first arrival rate is given as 18 ships per week. So lambda will be 18. Service rate is given as 6 ships per week. So our mu value is 6. Capital N value is 6. And C value is 4. Number of docks is 4. Number of ships restricted inside the harbor is 6. That is why N is 6. So rho will be lambda by mu, it is 18 by 6. So it is 3. Here rho by C is 3 divided by 4. So it is not equal to 1. Hence, we will be using this formula, that is summation C is equal to, summation N equal to C to minus, N equal to 0 to C minus 1 rho power N. So let us substitute those relevant values in this formula. So we will open a bracket. N is equal to 0 to C minus 1. Rho value is 3. So 3 to the power of N divided by N factorial plus rho power C. That means 3 to the power of 4 times 1 minus rho by C. Rho by C, we know it is 3 by 4 or 0.75 to the power of capital N, that is 6, minus C, that is 4, plus 1. This entire thing divided by C factorial, that is 4 factorial, times 1 minus of rho by C, which is again 0.75. This whole thing under flower brackets, we will be taking to the power of -1. So in case if we, once we start calculating this, we will land up with, after substituting N for 0, first term will be 3 power 0 by 0 factorial, which is nothing but 1. Second term will be 3 power 1 by 1 factorial, which will be 3. Third term will be 3 square divided by 2 factorial, so it becomes 9 by 2. Fourth term, that is 3 power cube divided 3 power 3 divided by 3 factorial, that will become 27 by 6. So C minus 1, so we need to stop till 3 only, plus 3 power 4 is 81, and inside the brackets we have 1 minus of 0.75 to the power of 6 minus 4 is 2, 2 plus 1 is 3, divided by 4 factorial is 24, and 1 minus 0.75 is 0.25. And then again, this entire thing will be taking the inverse of that. And if we calculate this, we will get the value as 0.048. That is the first one. Now let us move on. Next is the average number of customers waiting in the queue. We have to use this formula because rho by C is not equal to 1. So we'll be using this formula. Now substituting all the values, we already have P naught value we calculated as 0.048 multiplied by rho. Rho is 3 to the power of C plus 1. C plus 1 becomes 5 divided by C minus 1, that is 4 minus 1, so 3 factorial, times C minus P, that is C minus rho, 4 minus 3 to the power of 2, inside the brackets, 1 minus 0.75 rho by C value, N is 6 and C is 4, minus 6 minus 4 times 0.75 to the power of 6 minus 4 times 1 minus 0.75. Now, once we calculate this, we will get the value as 0.30375, And since it is about number of ships, we'll write ships here. Let us move on further. Now, for calculating what you call LS value, we need to find out what you call lambda, effective lambda rate. For that, we need to find out PN value. So let us see what is our PN value. Rho power 6, that is 3 power 6. P naught we calculated as 0.048 divided by C factorial. So it is 4 factorial. And then C to the power of, that is 4 to the power of 6 minus 4 is 2. So if we calculate this, we get the value as 0.0911. So let us move on. Now effective lambda rate we can find out. This will be equal to, and lambda is 18, value of lambda, 1 minus of this, whatever we calculated above, 0.0911. So if we calculate that, we get 16.3602. Now, average number of customers waiting in the system can be calculated as LS, that is LQ. That is LQ we calculated as 0.30375 divided by, oh, sorry, not that, just a moment. Yeah, so 0.30375 plus effective lambda rate is 16.3602 divided by mu, that is 6. If we calculate this, we get 3.03045 ships. That will be the average number of customers, means here it is ships actually. Next, we'll proceed. Average number of, average waiting time of customers. Here, everywhere customers, wherever it comes, it is actually talking about ships. Customers is in general. In this case, it is ships. So WS equal to LS. LS we calculated as 3.03045. I think there we need to write ships also. I already wrote. So divided by effective lambda rate is 16.3602. If I calculate this, we get 0.0186 weeks. And by multiply by 7 days in a week, we get 0.13 day as the average waiting time. I'm sorry, I think I made a mistake here. I'm sorry. Not this. WS. That 3.03045 divided by 16.303602 you will get 0.185 weeks. And if I convert it, I will get 1.3 days. Then average number of waiting time of customers in the queue, WQ, and that will be LQ. LQ we calculated as 0.30375 divided by 16.3602. If I calculate, we will get 0.0186 weeks. And multiplying by 7, we will get in terms of days as 0.13 day. So that is the solution for this particular problem.